Hello. Here we have question 4 of the 2018 MMPC round 2, and it looks like a number theory problem. We want to find the number of ways that we can write a multiple of 8 as a difference of odd squares. And they even give some examples, right? F of 8 equals 1 because 8 can be written as 9 minus 1, and that's the only way. F of 24 equals 2. It can be written as 25 minus 1 and 16 minus 9. And those are the only two ways. So our questions are, find f of 120, find the, oops, I miswrote this one. This would be possible, but not quite so hard. Find at least x so that f of x equals 8. And then third, we want to show that it's possible to get any possible natural number as an output of this function. So there's two ways that you might want to approach this. One is to just compute a whole bunch of differences of squares and try to find a pattern. And the other is to dive in with generic odd squares and see if it can simplify. So I'll start with that second way. Let's just calculate. Because when I hear the phrase difference of squares, I think about how nicely it's going to factor right away. So this will equal the difference of these numbers times the sum of these numbers, right? So it's going to be 2n minus 1 minus 2n plus 1 times 2n minus 1 plus 2n minus 1. And so my 1's are going to add to 0 here. I'm going to be able to factor a 2 out of both expressions. So I'm going to get 4 times n minus m times n plus n minus 1. And notice that n and m could be n and m could be any natural number. If n and m are the same parity, either both odd or both even, then exactly one of these two numbers is even. And if n and m are different parity, then also exactly one of these two numbers is going to be even. So in other words, this is why the domain of f has to be multiples of 8. This number is already a multiple of 4, and one of these numbers is even as well. So this number is always a multiple of 8. Okay. And now that I've written it as a product instead of as a difference, right? I can think about how many different ways I can represent the same number. And, oh, okay, well, kind of makes sense. Let's do it for 120 as an example. And because it doesn't make any difference, I'll assume, without loss of generalization, that n is bigger than m, and I'll even say, let's say n equals m plus k. So k is the difference between n and m, right? So I can think about n minus m as k, and I can think about n plus m, I guess, as 2n minus k minus 1. I'm not sure if that's the best way to write it down. But anyway, if x equals 120, then x divided by 4 is 30, right? So k is going to be, like, the possibilities for k is going to be all the divisors of 30. So it could be 1, 2, 3, 5, 6, and then I guess 30 divided by these numbers, right? So 5 is already listed, 10, 15, and 30. Okay, so probably not all of these are going to give me a different answer, are going to give me a different valid number for n and k, but let's just see what we got here. So if these are k, then my 2n minus k minus 1 is going to be the same numbers in the opposite order. And then I can calculate my my n that way. So if this number is 2n minus k minus 1 and k is 1, then n is going to be 32 over 2. It's going to be 16. I guess I can get my m also. M is n minus k, so m is 15. So I could even double check at this point. 120 should equal 31 squared minus 29 squared. And if I'm really good with computing squares, I can check this by hand. But it's a little hard, so I'm not even going to, I mean, I guess I could write it as a difference of squares now. So 2 times 60. Yeah, so good. Right, so if k is 2, this is n. So we're going to have this number plus 3 divided by 2 gives me 9 and 7. 10 plus 4 divided by 2 gives me 7, and then 7 minus 3 is 4. Okay, we're going to add this number plus 6 divided by 2 gives me 6, and then 6 minus 5 is 1. So just to write down another example, this one's going to make sense. 2 times 6 minus 1 is 11, so this is 11 squared minus 1. And that should be the end of it, right? If I start to go to the next row here, right, then 2n minus k minus 1 equals 5 when k is 6, right? That's going to mean that 2n would equal 5 plus 7 would be 12, so n would be 6 again, but then what would k be? 6 minus 6 is 0. And that would mean that m is 0, but m is supposed to be a natural number, right? In other words, if I plugged in 0 for m, I'd have a negative 1, and then it wouldn't be a difference of odd positive squares. So when you think about this, maybe I should have written this down already. If k is bigger than n, then if k is bigger than n, even bigger than or equal to, then m is going to be less than or equal to 0. I don't know if I had to say that. I was thinking if I had to say that. So we don't want that to happen, right? We're not going to count those solutions. So, so valid choices for k include half of the divisors of 30, right, in this case. And that's always going to be the case. Unless x over 4 is a perfect square, right? Maybe we'll have to deal with that separately. What if x over 4 is a perfect square? Because then we're going to have an odd number of possible k's. If it was a perfect square, then these two numbers would be equal, and then these two numbers can't be equal, and would not be an integer. So yeah, so this is never going to be a perfect square. Maybe you should write all that down for a full solution, but just to get the ball rolling here, I'm going to say f of x is 1/2 number of divisors of x over 4. Okay, so that's the big result of this kind of calculation inspired by this one special case. So in particular, I just counted up f of 120 equals 4, and the justification is all the work we did here. Find the least x such that, well, you know what, this already, this almost solves problem 3. We just have to show that numbers x over 4 could have any integer number of divisors, right? So, how should I say? You guys should be familiar with how to count the number of divisors of an integer by first writing the integer as its prime factorization, and then a divisor is going to be any number written where all of these exponents are less than or equal to what they are in the case of x. So the number of divisors, right, you're going to have P2 plus 1 choices for the number of factors of 2 of the divisor. It could be an odd number, or it could have anywhere up to P2 factors of 2. And the same thing for each prime factor of x. And so, so the number of divisors is going to be a product like this. So now we can say, if x over 4 has 16 factors, right? Then, well, okay, we have to think about what these numbers are going to be. How are we going to write x over 4 as a product of prime factors? And well, 2 to the 15th is certainly one possibility. It's probably not the smallest, right? I have to think about ways to express 16 as a product, and then of course I want to put the largest numbers of the product as the exponents of the smallest possible prime number. So 2 to the 15th is one possibility, and if it's 16 times 1 times 1 times 1, right? And that's obviously going to be smaller than any prime number to the 15th. If I write 16 as 4 times 4, then it could be 2 cubed times 3 cubed, right? If I write 16 as 4 times 2 times 2, then it could be 2 cubed times 3 times 5. And best yet, if I write 16 as 2 times 2 times 2 times 2, then x over 4 is going to equal 2 times 3 times 5 times 7. And that's the smallest number because 8 is smaller than 7. Huh? No. Huh. This is the smallest number because 4 is smaller than 7. 8 isn't smaller than 7 anyway. Yeah, so 8 times 3 times 5 is definitely smaller than 2 times 3 times 5 times 7. Right. On the other hand, 9 is bigger than 5, so this guy's bigger, and this guy's just way bigger. I barely even have to calculate it. Okay, so this is the smallest for x over 4, so that means that my answer to question 2, x equals 4 times this number, so 2 to the 5th times 3 times 5. And I'll leave it in factored form. My answer to problem 3, I'll just say number of divisors of, let's say, whatever, 2 to the P2 equals P2 plus 1. I mean, let P2 range over all integers, and some of them we're going to be able to get any number here. So I don't like that. Let me give an explicit example. How about, yeah, okay, let's have one P2, and then, so f of 8 times 3 to the k is going to equal to k. And that's going to be true for any n and k that's supported by these calculations. So, so that's one way, by constructing the example, one way to find that the range of f is all natural numbers. Okay, so a couple things were not discussed, were not like fully proven. This might not be a 10-point solution yet. I think we'd have to say a few more words of supporting why is half the number of divisors of x over 4 always going to be f of k. You know, we can see that like each of these different k's is going to give us an n and an m. Is it ever possible that we'll have the same pair of n m's repeated? You might want to say a few words to show why that's impossible. I mean, it seems pretty easy because n is always going to be bigger than m, and the k's are all different. So, so I think we should be okay. Probably not much left to say. If you had approached this by starting with a lot of number examples, you'd probably be able to solve this one. You might get an answer without justification for this one, or without full justification for this one. And you might even be able to show this one by following some patterns. I thought about a way to do that, and it was harder to explain than going through like this kind of more direct calculation. We'll save that for an offline discussion, I think.